again and welcome. What I'm going to do in this is solve 3 horizontally launched projectiles and show you how you can solve these problems using the kinematic equations. The other thing I'm going to show you is how to account for the x and y coordinates of velocity and how we can find the impact velocity at the ground. So as I do the problems, they're going to get progressively harder, so you can see how this works out. So I just found some web-assigned questions like this, and I'll just solve some of these as an example. So your web assigned will be a little different, but they're going to be, of course, similar to what we'll see here. So what we see, question 1 is we have a tiger leaps horizontally from a 5.5 high rock with a speed of 3.75. How far from the base will she land? So as always, do a diagram. So here's our situation. So let me just take a quick peek back. Our cliff is 5.5, speed 3.7. So our cliff is 5.5 meters high, and the person is running off with a speed of 3.7 meters per second. So if we think about it, the person's going to do something like this. So the question is asking for how far from the base, like that. So notice that I started labeling this as x. So this is an x measurement. I want x, not y. This is a y measurement. So if you need to write it in, go for it. Or dy, whatever works for you, of course. Now, I know that it's horizontal because it specifically says in the problem, a tiger leaps horizontally. Sorry, I drew a person, I think. So it's horizontally, that's the key word. And when I see that word horizontally, that allows me to draw a horizontal arrow right here, which also means if the start of this, that's my Vx. So what I like to do is organize my information in a chart, x and y. So my initial velocity is going to be all horizontal, so it goes here. My initial y velocity is 0 because there is no angle, number 1, and it's also horizontal, so it implies no up or down. So I can get that from the problem. I don't know x, and that's what I'm solving for, so I usually put a question mark. And technically I don't know time either, because remember, Vx is equal to x over t. So I'm actually thinking about this equation and what I have, so nothing really. But I'll leave it blank because, spoilers, I'm going to find it to time over here. That's how we're going to relate the problem. Okay, so let's look at the y. So we have y height as 5.5 meters right now. Now the object's going to be falling, so I could throw in that negative sign to represent the fall, the downwardness. Acceleration is given in the problem. It's under free fall, so I will use the negative 9.81 right here. So right now, that's all of the information that I have. So at this point, you get a little stuck because you're like, oh no, I have 2 unknowns here. This is all I have here. But remember, time is how we're going to connect these two. So what I'm going to do to find time is see if there's a kinematic equation that I can use to find time, and then plug into here, at which I can do that. So in other words, like I said, there's 2 steps to these problems, and the key usually is time. If I can find time in one, I have it for the other. And as a check, it's going to take the same amount of time to fall 5.5 as it is to go here. So in other words, the time, if I find the time in the y here, I have found the time in the x, so this is okay. So that's exactly what I'm going to do. So if you notice, I'm going to find time in the y first. And here's the equation I'd like to use. I'll keep it consistent, even though okay, so I'm going to use this equation because as you can see, we have initial, acceleration, displacement, and we're looking for time. So watch how this looks. Now I use delta x here to represent displacement, but you can put y in here. In fact, I'm totally fine with that. But notice I am going to put a vertical measure here. So I must be careful. I must use the negative 5.5 as my displacement. 0. Just like that. Now I'm going to solve for time. So a shortcut is, if you notice, that this whole term goes away because this is 0, which is good because we don't want this to be quadratic, because otherwise it might be. So that's actually a good point. So what you get from this, I'm just going to go ahead and solve for time. So just trust my algebra. Assuming I don't make a mistake. Please let me know if there's an algebraic mistake in my video. I would greatly appreciate that. So when I do this out, I get 1.06 seconds. So that's how long it took to fall vertically. That's basically what we calculated. This is the fall time to do this. Now, during that fall, we were also going horizontally. So I can actually plug that in right here, which is very nice. So now that I have time, I can find my range, or my x, using time and y. Vx is equal to x over t. Vx is the 3.7 meters per second. X is what I'm solving for. 1.06 seconds is the time. So I'm going to do that times 3.7 to get x. And that's going to be in meters, like this. And that represents how far this goes. So this number we calculated is this number right here, 3.92 meters, like that. And just to double check, when we put it in, that is correct. So you can see that is the correct answer. So that's the process we're going to use. I'm going to do it again much faster, so you can kind of get an idea of how this works and see how I'm connecting everything together. So the next question is a diver is running 1.5 meters, and it dives out horizontally off the edge of the cliff. And 3.4 seconds later, it reaches water below. How high? How far? This problem is actually easier, to be honest. And the reason is because they give us time. The question asks how far and how high. And we know that the diver will make this motion. So again, this is a horizontally launched projectile because the diver dives out horizontally. So that's our key word. So I'm making the diver a circle here. We know the speed there. But we also know how long it took. So that is in the problem as the 3.4 seconds later. So the time it took to make this motion is 3.4 seconds later. Here we go. Vx is the 1 meters per second. Time is 3.4. And we're looking for x, so that's actually pretty straightforward. We have vi, remember, for a horizontally launched projectile, 0. We have acceleration, so these are two things not given but implied. We have time. Pretty good. This is pretty easy now because I basically have the information here because we have Vx is equal to x over t. 1 meter per second equals to x over t, which is 3.4 seconds. X is 3.4 meters. That was simple enough. This one. So for horizontally launched projectiles, I like this equation because you can simplify it because it's always 0. So if you want, you can actually just skip ahead and do this for horizontal. So that's really nice. Because of that, it's much more simple. So plugging in my numbers, a is for acceleration, 3.4 seconds squared, 0.5, 9.81, 3.4 squared, 56.7. Now it's negative because it fell that far. So if we enter those in, So we said what, 3.4 here? How far from the base? So it didn't say displacement, so I'm just going to go ahead and write it as a positive value here. Oops. Did I submit it right? Oh, I think I graded it already. Sorry. Let me redo this. Give me 1 second. Okay, I fixed it. I switched the numbers by accident, so that should work now. There you go. Sorry about that. Yeah, because this one's asking for base and this one's for height. So there you go. So that's how you solve this one. Okay. So here is this one. So we're asking pretty much the same question. This is a horizontally launched projectile because what's going to happen is the plane is moving, so when we drop that package, it's going to carry that motion, just like this diagram suggests. And I'm going to take an extra step here and go into this part, because if you notice, because I like this visual right here, that when it strikes the ground, it's going to have two velocities. So if I put a force sensor or a motion sensor right here, it's not going to measure Vx, it's not going to measure Vy, it will measure the two of them. So notice that it makes a triangle. So I'm going to show you how to solve for the impact velocity at the bottom here. So this whole first part should be pretty simple. It's this next part that's going to be sort of difficult. So I'm actually going to do it right on this one so that we can see what's going on here. So here's our cargo plane. It's going horizontally, so there's the word horizontal again. So this is our Vx. 223 meters per second squared. We're at a height or altitude of 900 meters. The question is, how much time does it take the package to reach the ground? So we're looking for time in this one. So this one's actually not too bad so far, because what we have is x, y, right? So always start by organizing your information. I cannot stress that enough. You will not see what's going on or what you need to do until you do this. So we have Vx as 223 meters per second. We don't have time and we don't have x. This one we have delta, I'll use y in this case, as 900. And negative for falling, we have a, it's negative 9.81. Again, these are a is implied, VIY is implied, remember? And that's it. But notice, since it's similar to what we did earlier, we can actually solve this using that shortcut kinematic equation pretty simply. So this problem actually looks really complicated, but it's actually not too bad. So if I solve for time here, so it's going to look like this. I'm going to go over here. So delta y is going to be 900. And then we solve for time. 900. I'm calculating now. 13.55. That's the problem. So it's not too bad, as you can see. So what did I get? 13.55? Yeah, not too bad right there, right? Okay, but I am going to do an extra part to this problem because I want to calculate V right here. So I'm going to calculate exactly oopsie. I'm going to calculate V in this problem, and since I only have 30 seconds left, what I'll do is I'll do it in the next video. I want to show you how to calculate an impact velocity.